Hi, my name is Andrea Roser. I'm a graduate student at Cornell University in Jesse Goldberg's lab.
Hi, I'm Jesse. I'm an associate professor in the Department of Neurobiology and Behavior at Cornell. And this is Raydong Chen, who's currently in Woods Hole, so he can't be here at this moment, but you'll be hearing from him later. And my lab is interested in neural mechanisms of performance evaluation. So imagine you're going out to play tennis, and you have this dream of hitting your forehand and your backhand like Serena Williams. But you can't really go out there and compare yourself to Serena Williams. If you want to evaluate the quality of the forehand you hit, if you compare yourself to your ultimate goal of swinging like her, you'll chronically be disappointed. So one strategy might be to compare your current forehand to your past forehand. In other words, was the current forehand that you just hit better or worse, or closer or farther to the Serena Williams goal than you thought you would be based on your recent forehands? And so in order to do that kind of performance evaluation, you need to have a predicted quality about how good your forehand is and a separate predicted quality for how good your backhand is.
In this paper, we are looking for the neural correlate of predicted performance quality. We focused on the ventral pallidum, or VP, a limbic structure with projections to VTA dopamine neurons. In mammals, VP neurons encode the predicted reward value of cues. So we wondered if songbird VP might analogously encode the predicted quality of specific song syllables. When we lesioned VP, song learning was impaired. And this motivated Raydong Chen, Pavel Puzuri, and I to record VP signals during singing.
Hello, my name is Raydong Chen. I'm a graduate student in Jesse Goldberg's lab at Cornell University. After demonstrating that VP lesions impaired song learning, we wondered what VP's function was during singing. We recorded VP neurons, including antigenomically identified VTA projecting neurons, in a paradigm where we could experimentally control perceived song error. Specifically, a zebrafinch song has many syllables. By distorting the auditory feedback of one specific target syllable over many days, we can trick the bird into thinking that his target syllable is low quality, whereas his other syllables are fine. It's kind of like if we experimentally made Serena Williams miss half of her backhands over a few days. If we recorded her brain activity, we could look for a neural correlate of predicted error specifically before she swings a backhand. Some neurons exhibited phasic modulations in firing rate immediately before the part of the song targeted with distorted auditory feedback. What's shown here, from top to bottom, are the sound spectrogram and voltage signal in one undistorted trial, one distorted trial, raster plot of neural activity separated into undistorted on top and distorted trials on the bottom, and rate histogram of all undistorted trials in blue and that of distorted trials in red. Everything is aligned to the target syllable time. As you can appreciate from the histogram, this neuron on the left exhibited a pause in firing right before the target time, consistent with a predicted quality signal. And the neuron on the right showed brief bursts right before the target time, consistent with a predicted error signal, as if this neuron is signaling you're about to make a mistake. Other neurons were auditory responsive and exhibited phasic signals immediately after the target syllable. This neuron fired in a brief burst immediately after the target syllable, but only when no distortion happened, consistent with a neuron that encodes a better than expected syllable outcome. This neuron was antigenomically identified as projecting to VTA and could therefore play a role in constructing the signals that we previously identified in VTA dopamine neurons. Finally, yet other neurons could exhibit temporally precise discharge during singing. This neuron on the left shows sparse bursts time-locked to specific syllables, while the neuron on the right exhibits temporally precise bursts throughout the song. To test where these diverse timing, error, and error prediction signals could be coming from, we used a retrograde virus to identify inputs to VP. We found many inputs. 3 particularly interesting ones were from the following regions. First, vocomotor, cortical, and thalamic areas known to encode precise sound timing. Second, an auditory cortical area shown by Michael Fee's lab to encode auditory error responses during singing. And third, collaterals of VTA dopamine neurons that project to the more dorsal basal ganglion nucleus, area X. This dopamine input was particularly interesting to us because dopamine-modulated plasticity of the timing inputs from motor thalamus or cortex could weigh sound timing representations according to their past error, resulting in an error-weighted timing signal, or equivalently, predicted error signal.
So, in summary, we discovered that a ventral pallidal region of the songbird basal ganglia is necessary for song learning, sends diverse performance evaluation signals to the VTA, and may, along with the more dorsally located basal ganglia nucleus area X, form an actor-critic architecture previously unrecognized in the songbird brain.